Oh, okay, never mind. A couple people do. I did record yesterday. I did, and it's posted. The day before, I recorded the first like 8 minutes. Then I had to show a YouTube video, and I had to change all my audio, and then I never got it back. But today I'm going to show a YouTube video, but I connected a tiny little Bluetooth speaker over there that will make me not have to connect. Because it's dumb. The computer only has one input, so this mic and the speakers are the same thing, and they don't. You got to undo one to do the other. I've tried that before, and I get a ton of feedback somehow. I don't know why, but it's not good. All right, yeah, the first minute is nothing, even though I didn't record what was important. Merry Christmas, Happy New Year, Happy Martin Luther King Day. All right, we didn't really go over these. We just barely started these, but you may be able to get this question right. The heating curve shown above. Let me clear all this and just make this quite a bit bigger. You're welcome. Whoever said that. All right, and once again, ignore the top because that was the answers to the previous problem. The heating curve shown above was generated by measuring the heat flow and temperature of a solid as it was heated. The heat flow into the sample in the segment blank will yield the value of the heat of vaporization. All right. Vaporization, whoops, it meant to do what? That's where we convert a what to a what? All right, a liquid to a gas. Okay, so as long as we know that, this heating curve is probably not that hard because right here it says liquid and gas, right? So the segment from D to E is the measurement of the heat of vaporization. It is the heat added, and remember heat and energy are pretty much the same thing. So the energy added to take all the liquid and end up converting it all to gas. You okay with that? I don't know why, but I find both those arrows to be some of my best I've drawn this year. Thank you. Okay, are you okay with that idea? We didn't really talk about heating curves yet. That's today, but they're not that bad. From A to B, it's a solid, and all the energy would go into raising the temperature of the solid. From B to C, it's where it goes from a solid to a liquid, and all the energy would go into melting. What did we call that fancy word? What would this be measuring? Thank you. It's the heat of fusion. Or why am I writing delta H? All right, it's change. What's H again? Enthalpy. All right, which is pretty much heat, if you remember, because the math all canceled all the other crap out. So they're all interchangeable, which is unfortunate in some ways, but actually kind of nice math-wise. Okay, so that would measure your heat of fusion. All right. From C to D, all you're doing, all the energy is just heating the liquid. Okay? And that's like right when the bell rang yesterday, I think. And I said, that's why your drinks, as soon as the ice is gone from your drink, it actually heats up pretty fast. But it'll stay cold for hours as long as there's still ice in it, because all that energy is going into here. Right? All right. Then D to E, we just barely said that's your delta H for vaporization. All right. And then E to F, you're just, all the energy is going into heating the gas. Okay with that? All right. Good? So that's, I think, all of the multiple choice that there is for Chapter 11 on this next test. It's a Chapter 11 combined test. I do that for a reason, because I really like the combination of 11, 13, because it's my birthday. Boy gets an A forever, as long as he earns one. All right, so this test, or this chapter's not super hard, hopefully. You got all those written down in your notes. Okay, so we did talk about that. We've talked about that. I think we're finally on, oh, you did that, we did that. Phase changes. We were here, and then we were, yeah, we were there. Okay, we were on this right when the bell rang. So I just talked through it again. If you're a note taker, I would draw this and label what's happening for each piece. So do you want me to repeat that? Okay. So let me make it bigger. Okay. So I'll pause. Well, I might as well repeat myself. Who cares? A to B segment. We are heating the solid. And there's no like term for that. We're just making the solid warm up. Okay? All right. B to C. We are melting, which does have its own fancy name, which is called the heat or delta H of fusion. Okay, that's the energy we are putting in to make the solid become a liquid. All right, from C to D, we're just heating the liquid. I know my writing sucks, but you're used to it by now. I mean, we are 4.5 months in, so get over it. All right, we're heating the liquid. No fancy name for that. And then D to E, it's boiling, or the heat of vaporization. Okay? And then E to F, tell your lab partner what you're doing. Okay, we're just putting heat into the gas to make it warmer. All the energy that goes in heats the gas. Okay. That's that. Like, it's nothing huge. You should know this. Like, my wife and I have thought about this for years. The temperature of a substance does not rise during phase change. Why do you think we've thought about that? That's a weird thing to fight about. Nope. It's because when she boils, yeah, you remember last year? When she boils mac and cheese, or like the potatoes, it boils over every single time. When I do, it never does. Because I bring it to a boil, and then I turn it way down. And it just barely bubbles. And she keeps it on high, so it'll cook faster. But that's not true, because what happens during phase change? The temperature of the water stays the same. And I'm not joking. We've argued about this. I, in fact, took my scientific measurement tools, and I showed my wife that the water stays the same, whether you have the burner on high or on low, and it just simmers. And you know what she said? She said, well, I don't care then. It must be the bubbles that cook it faster. I was like, okay, I love you, but that is scientifically untrue. Can't prove it, so I don't know what to do, because you can't. I don't have a tool. Yeah, she doesn't buy that stuff. She's wonderful, but we fight about that in sports. Okay, the next, and if I remember, the last main topic of Chapter 11 is called vapor pressure, which we've already talked a teeny bit about. But it's in this chapter because the vapor pressure is affected greatly by the intermolecular forces between something. So, as discussed last chapter, vapor pressure is the pressure of a gas above a liquid. Liquid substances of low molar mass and weak IMF tend to have high vapor pressures. Now, this is tricky. A high vapor pressure means they evaporate easily. Okay? It means they have a lot of their gas above their liquid. Yes, sir? Yeah, for sure. Rubbing alcohol evaporates very quickly. I have some methanol. Yeah, they both burn. So, like, they're also called volatile. It's the same idea. But volatile means that vapor is also flammable. Methanol, I don't know, like, we use it in the lab once in a while. When it spills, I just wipe it up with my hands because A, it kills everything on my hands, like bacteria. And B, it feels cool because it's like super cold. When it evaporates off of you, you're like, wow, I feel clean. All right. increasing temperature will increase vapor pressure. Why? So this is a discussion point in that little reader I gave you. You don't have to write your answer, but please take a minute and discuss. Why? Hopefully we're good on this. Why will it increase the vapor pressure? If I was in this class, I would draw it personally. Which one of these is a high vapor pressure and which one's a low? All right, this is a high vapor pressure. Okay. That's probably my best lid of my life, too. I mean, I am on today. You know, actually, I've struggled to draw my line straight so far with this new thing. I can, but then I got to select the color and the width, and it's just a pain in the butt. But here we go. Are we all right with that? High vapor pressure means a lot of gas above the liquid. It means low is a little bit. Okay. So increasing temperature will increase vapor pressure, all right, because more of the liquid will be converted to a gas. That's really all. As you heat it, more become gaseous, all right. Now, I'm not sure what screen this will show up on at first, but we'll get it over here. And I don't know if this Bluetooth speaker will work very well, but we'll figure stuff out. Hey, that's not bad. Hold on.
Pulled down by gravity. The air above us creates pressure.
I feel like this guy would be a good speaker at General Conference because it's so relaxing and could put me to sleep in a heartbeat. Oh, where's the thing? Okay, hold on. We'll start. Oh. Okay, this is a pain in the butt. It's right on the thing. Hold on.
We know that boiling is strongly influenced by atmospheric pressure. Pulled down by gravity. The air above us creates pressure, and that makes it difficult for bubbles to form and boiling to take place. We can think of atmospheric pressure as the collision of air molecules against the surface of the water. That's the pressure. The more collisions, the greater the pressure. The water molecules can create pressure when they hit the liquid. These fast-moving water molecules equalize the air and create pressure. We call it vapor. In a way, the water molecule is pushing, sliding the air molecule. This reduces the amount of pressure felt by the water. Back to boiling. Textbooks often state that when the vapor pressure equals the atmospheric pressure, boiling takes place. This is called the boiling point. Think of it this way. Atmospheric pressure pushes gas, and that makes it difficult for the water molecules to spread out and form a bubble. So when the vapor pressure increases, molecules from the liquid escape, and they push against the air molecules. And effectively,
So what's the number one way we make vapor pressure increase? We heat it. Okay?
by either increasing the vapor pressure or decreasing the atmospheric pressure. Either way, once the vapor pressure and the atmospheric pressure are equal, you reach the boiling point.
That's something you definitely need to know. Go ahead. Yeah. When you put water in boil, because the pressure above it goes almost to zero. Okay, we don't have any perfect vacuums. Goes almost to zero. And so then the vapor pressure is almost the exact same as the new atmospheric pressure, and it just pretty much instantaneously boils without heat. Yeah, you could touch it. I mean, if you could get in that vacuum, it would just feel cold, but it would just be bubbling. Okay, this is also the reason why water in Utah boils at a lower temperature than it would at sea level. And it's not that big of a deal. It's just a couple of degrees. But in Utah, we have less atmospheric pressure than they do at sea level. So we have different vapor pressures. Then we have a different boiling point.
Therefore, they have different boiling points. This has to do with how strongly the molecules are attracted to each other from the liquid. The more strongly they're attracted contracting, the less the vapor pressure, the more difficult to boil. Therefore, the higher the boil.
Diagram, but this is a different format. These are of utmost importance, I should say, for the AP test and for your test. And the good news about that is they're not that hard. All right? So this was in that little video, but it's a definite thing you should know. Boiling point is when the vapor pressure of the liquid matches the atmospheric pressure. Okay? We typically get the vapor pressure to match it by heating it. Okay, next, these phase diagrams. They show the relationship between temperature, pressure, and the state of matter the substance is in. The lines represent the boiling and melting points under given conditions. I've actually seen these on the ACT before. And they didn't expect you to know, like, why it is the shape it is. They just expected you to look at a chart and be able to reason through it. The ACT loves charts and tables. All right. So, what you need to know. You need to know this is when things are solid. All right? I guess it just says it right there. Right here. This is the solid section, which should hopefully make sense. It's when it's cold and under a lot of pressure. Okay? That's when the thing will be a solid. Then here's the liquid. All right? And that's kind of the between phase. All right? And then here is your gas. Typically, as the temperature increases, we move from solid to liquid to gas. Now, these look sort of weird how they are, but if I do this, they'll sort of make more sense. About to sneeze again. Pretty much, right? And it starts as an ice, or solid, or ice. Then it goes to a liquid, then it goes to a gas. Okay? When we start to add a lot of pressure, things change quite a bit. And that's why at the bottom it might look weird that, hey, we're just starting as a gas. But down here, we almost have zero pressure. Up here we have a lot, zero temperature, high temperature. Now, what Boyd is saying, and this is in the book, it's a long explanation, but why is this going that direction, correct? You can add pressure and turn things, decrease pressure and turn things into a gas. But water has it sort of backwards. You'll notice both of these, their slopes are increasing. Water's is decreasing, and that's because of its strong hydrogen bonding. When we take the solid water, it lines up in a nice crystal with lots of empty space. All right? If we pressurize that solid, it actually will squeeze them together, and then water actually becomes a liquid. It's one of the few that do that. You have to have very strong hydrogen bonding for that to happen. Now, right here it says the phase diagrams for water and carbon dioxide should be understood. Carbon dioxide behaves normally, water behaves abnormally. There's a section in your book. It's only like one paragraph, so it's not like I'm asking you to spend an hour. But please read about phase diagrams and the water. Okay, now there are a few points on here that you need to know. Let me see if they're on this next. Okay, so we'll just do them over here. Anytime along this line, we're going from a solid to a gas. Does anyone remember what that was called? Sublimation. Okay, you need to know that term, and you need to know that YX segment could represent sublimation. That's very typical on how they ask the question. They give you a segment and ask you what's happening during that segment. All right? From X to Z, that segment, we're going from a liquid to a gas. So this would be defined as the boiling point. Okay? It's the pressure and the temperature at which the liquid converts to a gas. You okay with that? All right. And then from a solid to a liquid, we would define, let's say this was Q, I don't know, whatever, X to Q, we would define that as my melting point. You okay with that? Yeah, you could have liquid carbon dioxide. It has to be above 5.1 atm. Well, room temperature is like right here. So it has to be like, see my straight line there, it has to be like 50 atm. So like, we are not in our coolers going to find liquid carbon dioxide. Okay, this point right here is called the triple point, and I'll go to the next slide. The triple point is the point at which all three states of matter can exist in equilibrium. Now, I can't describe what that looks like because I have no idea. Those conditions exist under pressures that are not normal and temperatures that are not normal, but it's where you can have the liquid, solid, and gas phase all together. Okay? They are indistinguishable. In fact, if you read more, go ahead. Yeah, they'd have to be cycling through an equilibrium 100% of the time. Okay? Pretty weird, but that's what the triple point is. Yeah. Right? Well, see, the thing is, there is a ton of pressure. They're pumping it in, I don't know the ATMs, but it's going to be a very high pressure in your nitrogen tanks. Now, when you get them out, it's no longer under pressure, right? And it stays that liquid for a while if you have it in a dewar or something. But yeah, when they collect that air, they are compressing it as well. So, good question. They also get it really, really cold. All right. The only other point that we need to worry about is this point right here, Z or D, and that's called the critical point. Okay. The critical point is where you cannot distinguish between the gas and the liquid. So that's why the line ends, but the thing still exists. You can't tell which is which. Okay? Solid and liquid are indistinguishable. Okay? How? I have no idea. It's like last night it was snowing and raining at the exact same moment on my drive home. But that's still not really like it is. But no, I may have said solid, but I meant liquid and gas. If I said solid, I'm sorry. Okay. Why do we never find liquid carbon dioxide in nature? It's not high enough pressure. At 1 atm, carbon dioxide exists as a gas. All right, describe the irregularities of the water phase diagram. That's where this line was inverted. All right, right here, this whole line is your irregularity, and that's due to hydrogen bonding and the crystalline structure of solid H2O. You actually squish it to make it become a liquid, which is the opposite. I don't know, because this doesn't really, I mean, it looks like it goes to 0. It will get extremely close. Say that one more time then. Yeah. All right, I think that's it. That's the end of chapter 11. Hopefully you feel okay with chapter 11. I've showed, I think, every multiple choice. Let me look at it. So you have to explain why the thing I'm going to say is the thing I'm going to say. So the boiling point of water, ammonia, and methane are 100, negative 33, and negative 164 degrees Celsius, respectively. So that's my statement. You have to explain why those three have such different melting, or it says boiling. It doesn't really matter. They all have similar mass, so that has nothing to do with it. Okay, next, at 26 degrees Celsius and 1 atm, chlorine is a gas, bromine is a liquid, and iodine is a solid. We did go over that. If you missed, that was the other video we talked about, which I did not record. But that had to do with what increases London dispersion forces. They're all in the same family. They're all diatomic. So they all have similar properties except for one major difference between each one. Okay, C. This one is actually not even from this chapter. And you've had it on a test before. Pretty much. Calcium oxide melts at a much higher temperature than potassium chloride. What was the intermolecular force that we have not talked in this chapter because we already had? Does anyone remember? It's ionic, but ionic had a special name. Lattice energy. Lattice energy, I think, was in chapter 7. And it said, hey, the greater the charge of the ion, and the greater, or the smaller the size of the ion, the greater the lattice energy. Okay, that's in chapter 7. And maybe I'm a jerk for testing chapter 7 and chapter 11, but I don't care. All right. Propane, and it gives you the formula, is a gas. And ethanol, and it gives you that formula, is a liquid at room temperature. You got to tell me why. All right. Next, a water and salt solution conducts electricity, but water and sugar solution does not. That has absolutely nothing to do with this chapter. That has everything to do with chapter 4. Why does salt water conduct? It has ions. Does sugar? No. They both dissolve. Salt dissociates. Sugar dissolves. Dissociated things make electrolytes. All right. A solution of ethanol has a boiling point of 79.2. Whereas pure ethanol boils at 78.6. That's going to do with colligative properties, which are actually in chapter 13. Okay, so that's your free response for chapter 11. You have to write them. No math in chapter 11 at all. Okay, we all right with that? Chapter 13 definitely has math. You have it there in your reader. Thank you. Oh. 11 and 13, they go sort of together because we've been talking about intermolecular forces and how things interact. Chapter 13 we'll talk about when things are mixed together. 90% of the solutions we'll talk about in chapter 13 are just ionic compounds in water. All right? And really, most of what this should say is quantitative properties of solutions. Now, we're going to get the word molarity again, which should be okay. We've learned that. We're going to talk about moles. We're going to talk about molality as well. And molality is new, but we'll be fine. So here we go. Solutions. In regular chemistry, we do this like for a month. It's my least favorite month of the entire year. And don't tell my friend. Solutions. They are homogeneous mixtures of two or more pure substances. Homogeneous means that they're all the same. So like when you put salt in water, it breaks apart, you stir it up. You can't tell, unless you put way too much in, you can't tell there's salt in there and water. It just looks like salt, or just like water, right? All right? In a solution, the solute is dispersed uniformly throughout the solvent. That's pretty redundant, because if it's a homogeneous, it's uniform throughout. Okay? Now, we should probably define, which we probably have before, but remember, if we have salt water All right, if we have a saltwater solution, salt is the solute, water is the solvent. Okay, did we do that in chapter 4 when we talked electrolytes? Okay, so that's just a quick review. All right, so we can have liquids and gases, we can have liquids and liquids make solutions. We never have solids make a solution with anything. Now, I know that we're putting a solid salt in, but once it dissociates, we don't call it solid, we would call it aqueous. All right, don't worry about that table much, but here we go. All right, the intermolecular force between solute and solvent particles must be strong enough to compete with those between solute particles and those between solvent particles. All right, so in order for something to dissolve, the water here must be more attractive to that ion than the ion is to its other ions. Okay? If something didn't dissolve, well, then the substance itself was more attracted to itself than it was the liquid that it was in. Okay? When we talk solubility rules. So this is also somewhat reviewed. A solution forms. As a solution forms, the solvent pulls solute particles apart and surrounds them or solvates them. Like, this is just, it's not bad. All right, if an ionic solid is soluble in the water, what I just said, it's because the ion-dipole interactions are strong enough to overcome the lattice energy of the salt. Oh, make this bigger. Oh, you would do that to me. Okay, so it will dissolve if the ion dipole is greater than the lattice. Now, you'll notice, by the way, how many waters are attracted to the Na and how many waters are attracted to the Cl. Because hydrogen bonding, well, I should say the polarity of the water molecule that makes these dipoles, it has some strength, but not stronger than Na and Cl. But if you have many of them, the many are stronger than the one. Yeah. Right here. It's not a double bond. It's just saying both H's are attracted to that partial minus. So, like, we would never actually call these bonds. It's just like a doubled attraction. How about that? It's okay. Yeah, no, we're not doing that. We're talking an intermolecular force now, not a real type of bond. So this is just saying both the hydrogens are attracted to the chlorine instead of just one. All right. Now, look how cute this is. Simply put, and this is pretty important. Simply put, three processes affect the energetics of the process when something dissolves. So the separation of solute particles. Okay, they have to be separated. Separation of solvent particles, that doesn't seem to make sense. But, like, if I was going to try and sit between these two boys right here, they'd have to make room, right? Just like if a chloride ion wants to move into water, the water actually has to physically make room. That takes energy. All right? And then the new interactions between the solute and solvent. All three of these things, they have some sort of energetic value. I love teaching with opera in the background. I know Benson, she likes it. Can you hear it? Yeah. Anyway, these three things will affect what we're going to do. Now, you don't have to know the math here. Okay, we're going to give you a value, and sometimes it's a positive, sometimes it's a negative thing, and just know it's because of the balance between these three things. All right, so, I don't know. I think I'm going to call it, because this if I get 2 minutes into this out of 5, we'll just have to redo it tomorrow anyway. So we are done. Just kind of